Here is how a research claim quietly gets too big. I trained two small networks on the same classification task. The second one is twice as many hidden units per layer. On one run, the wider network scores 92.33% on examples it did not see while learning. The smaller baseline scores 88.33%. That is a 4 percentage point improvement. If you saw only that result, the bigger network wins would feel reasonable. You might write the graph, change the default, and start explaining why the extra capacity helped. But that 4-point number came from one random seed. So before making a bigger claim, I repeated the experiment. First, make the question precise. The vague version is, bigger models are better. The testable version is, on this fixed task, changing the hidden width from 8.8 to 16.16 should improve held-out accuracy. Held out just means examples kept out of training until the final check. The baseline and the wider model see the same training examples. They are judged on the same hidden examples. And the only intended model change is width. That last sentence matters. If I change the width, the dataset, the metric, and the training schedule all at once, a higher score cannot tell me which change mattered. A useful hypothesis is not a confident sentence. It is a sentence that tells you exactly what result would make you revise it. Here is the complete local experiment. I generate 600 noisy 2 moons points with data seed 20260,806. 300 are training examples. The other 300 are held out. Both networks train for 200 epochs with a learning rate of 0.05 and batches of 32. For every seed, I give both models the same mini-batch order. Then I change the random seed and do the pair again. The metric is held-out accuracy. The run table is fixed in advance. Seeds 1 through 20, no shopping for a nicer seed, and no stopping when the chart looks flattering. This is the difference between fixing a seed and studying seed variation. A fixed seed lets another person repeat one run. A list of recorded seeds lets you see whether that run is typical. Now open the first result, the one that made the claim look exciting. At seed 12, the 8.8 baseline gets 88.33% on the held-out set. The 16.16 network gets 92.33%. The gap is exactly plus 4.00 percentage points. Would you adopt the wider model? Maybe. The result is real for that run. It is also incomplete evidence. A random seed controls things like the initial weights and the order in which training examples arrive. Those choices change the path the optimizer takes, even when the written hyperparameters look the same. So the honest question is not, can I find a run where the wider model wins? We already found one. The question is, how much does the result move when I repeat the same fair comparison? Here are all 20 paired runs. The blue points are the baseline. The red points are the wider network. Notice what the single headline hid. The lines cross. The wider model wins on some seeds. The baseline wins on others. Several pairs are effectively tied. The comparison is paired on purpose. Seed 7 for one width is compared with seed 7 for the other width, using the same task, split, and mini-batch order. That removes a chunk of irrelevant noise. It does not make the experiment deterministic. It makes the width comparison fairer. This is why the best run is a danger summary. It is selected after seeing the distribution. The other 19 runs are not inconvenient leftovers. They are the information that tells us how often the headline appears. The 20 pair differences average to plus 0.63 percentage points. The sample standard deviation of those differences is 1.62 points. Using the recorded run set, an illustrative 95% interval for the mean runs from minus 0.12 to plus 1.39 percentage points. The interval crosses 0. That does not mean the wider network is useless. It means this experiment does not justify repeating the 4-point headline as if it were a stable fact. The best seed was plus 4. The average evidence is much smaller, and the uncertainty still includes no improvement. The basic statistical reason is simple. If the variation is described by a sample standard deviation, the uncertainty of the mean scales like south divided by the square root of the number of runs. More runs do not magically reveal a universal truth. They make the estimate less hostage to one draw. This is a deliberately small, synthetic demonstration. It does not prove that wider networks never help. It does not reproduce a published benchmark. And 20 seeds are not a magic number for every project. The narrower conclusion is the useful one. On this task under this protocol, one lucky-looking run was too weak a basis for a 4-point claim. That boundary is consistent with the research literature. Henderson and colleagues showed why variance and non-determinism make deep reinforcement learning results hard to interpret. Colas and colleagues explain how too few seeds can distort comparisons. BERT fine-tuning experiments found that both weight initialization and data order contribute to out-of-sample variation. And the NeurIPS checklist asks authors to report training details and error bars from multiple runs. The lesson is not always run 20. It is measure the variation that your claim depends on, then make the claim no larger than that evidence. For your next AI idea, copy this loop. Write a question that can lose. Choose a baseline. Change one thing. Seal the held-out metric and stop rule. Then repeat the paired experiment across a recorded set of seeds, save every raw result, and report the average and spread. If the effect survives, you have a stronger reason to investigate it on more tasks and with an independent reproduction. If it disappears, you have still learned something valuable. The bigger claim. The first AI research field guide is a live, 10-page PDF built for this exact finish line. One bounded question, one fair comparison, saved seeds, raw outputs, and an inspectable result. It is linked in the description if you want the paper-sized version of the workflow. Your experiment does not need a bigger claim. It needs enough repeats to show what the claim can honestly carry.